So at the top of this page, we have a couple of notes about the linearity principle, and they're kind of important. They're sort of like, don't forget, the linearity principle only applies to homogeneous linear differential equations. So if I give you an equation that is not homogeneous, then it doesn't apply. You can't jump to the same conclusion. And then the other thing that's worthwhile noting, if you have a homogeneous linear differential equation, remember that would be something that looks like dy dt equals some function of t times y, then the most obvious solution for this, something that is always true, is y equals 0. And so sometimes, in mathematics we have kind of a flippant way of referring to those sort of solutions. We refer to it as a trivial solution. So another way of saying it is there's an obvious solution. And y equals 0 is the obvious solution. We might refer to it as the obvious equilibrium solution as well, right? So all homogeneous differential equations can be solved analytically by using our old pal, the separation of variables. So this is why we've been looking at these homogeneous linear differential equations, and we've been seeing them and thinking, oh, they don't look so bad, because we know how to use the separation of variables technique. And so down with this example, we see a separable linear differential equation. All I'd have to do is kind of divide both sides by y and then integrate both sides with respect to t, right? And I just have to integrate cosine on one side and integrate 1 over y on the other side. So we know it's doable. So this is definitely linear. So I'm just going to make a little note of that and say this is definitely linear. Oops, not linear, linear. And it's linear because the a of t equals cosine t, and it's also homogeneous because b of t in this case, there's no extra term over there, equals 0, right? So that makes it nice and easy. So we recognize that it's linear, we recognize that it's homogeneous, and we know that we could use the separation of variables to solve this thing. So that's what we're going to do. So as I mentioned, we would move the y to the other side, and so we would have y dy, and then move the dt in our kind of sneaky cheat little way, and integrate both sides with respect to t. So on the left-hand side, we're integrating, dt, there we go. We're integrating, 1 over y, 1 over y dy, and on the right-hand side, we're integrating cosine of t. And neither one of these are terribly tricky for us. I'm going to group my constants on the right-hand side. The integral of cosine, remember, is sine of t. And so I'm going to group both of those constants together, call it C1. Now you'll notice over here that I do the formal integral for 1 over y, and I include the absolute values, even though, as we've seen in other examples, it doesn't really matter all that much. It kind of takes care of itself. So I need to get the y by itself, so I'm going to exponentiate both sides. And when I exponentiate both sides, I'm going to exponentiate each one of these, say e to that power and e to that power, and I wind up with just absolute value of y, and on this side, e to the entire power of all this stuff. And a shorthand way that mathematicians will often write this is writing exp, and then parentheses. And then everything inside the parentheses is e to that power right here. So it's just a way of not having to avoid writing the, the superscript smaller upstairs. Now the nice thing about e to a power is, as long as this stuff is real numbers, the output is always going to be positive. So I can just kind of ignore the y values, or excuse me, ignore the absolute value bars, and rewrite this as y equals e to the sine t times e to the c1 by using my rules for exponents. And e to a constant is itself just a constant. So really, my general solution is just, I'm going to move this constant out front and call it c, just for general, c e to the sine t. And this right here, that is my general solution, right? And it's a general solution because we have that constant due to integration. And that is the general solution for this linear homogeneous differential equation. And of course, there's an infinite number of particular solutions that we might choose to take a look at. So I'm just going to grab this and pull it off to the side here and say, imagine all these particular solutions. So a particular solution might come from when you let y of 0 equals 0, right? And so if y of 0 equals 0, then you'd be taking e to the sine of 0 power, or excuse me, e to the power sine of 0, and sine of 0 is just 0. So this is 0. That means c, we can't really figure out what c is, but it turns out that c would just be 0 in that case. So we have all of these interesting things. Y equals 0 when c equals 0. Y equals e to the sine t when c equals 1. And of course something like y equals 2e to the sine t when c equals 2. And so we can kind of choose different values for c and get all the different particular solutions that we could possibly want. And we can graph them down here and see what they look like. And so paying attention, you can kind of get a sense of, what the initial conditions will yield, what kind of solutions they'll yield. And we can see what these might look like. Each one of these curves is a different initial condition. Each one of these is a different particular solution. And so for this top one here, I'll kind of highlight it in green. This top one here, this is the particular solution that's associated with right there where the c value is equal to 3. The initial condition right there is telling us 3. And so there's all kinds of different initial conditions that we might put in. And we can check with Maple and kind of see what's going on with Maple and see how that works in Maple. And I've got the Maple file pre-made for this this section so that you can kind of see and go along and see where the graph is coming from. But what about those non-homogeneous cases? What happens in the case where we can't do the technique of the separation of variables? What happens if this were cosine t plus y plus t? We'd be dead in the water. We wouldn't be able to factor anything out. We wouldn't be able to do that kind of trick of moving the y's to one side and the t's to the other. So what would we do in that case? Well, that's what we're going to take a look on the next page. And so we're going to consider a non-homogeneous linear differential equation that's containing an associated homogeneous linear differential equation in itself. So this is what a non-homogeneous differential equation looks like. So this whole thing, everything over there, that's the non-homogeneous differential equation. But we're going to kind of treat it as though it sort of contains this part, which is homogeneous. Right? So we're going to be a little kind of sneaky about it, and we're going to use what's referred to as the extended linearity principle. And in my haste to make little jokes, now with extra linearity for long-lasting flavor. Okay, haha. The general solution of a non-homogeneous equation, okay, general solution, is the sum of the general solution of the non-homogeneous equation and, of the homogeneous equation and one solution of the non-homogeneous equation. Now, hold on a second. The general solution of this thing, the general solution of this whole thing right here, is just the solution of the homogeneous part, right? And one solution, now notice it doesn't say the general solution, one particular solution of the non-homogeneous equation. So what we have to do is come up with the solution to this thing, which we already know we've got the techniques for being able to solve, right? And then we have to come up with one particular solution for the overall. Okay, in theorem form, if you want to think of it this way. If you know something is the general solution for the homogeneous part, right? If k times y sub h is the general solution for the homogeneous part, And y sub p is any particular solution of the entire non-homogeneous equation. Now that would be everything, the whole big thing. Then the sum of those two, right? And so putting the language together, it's the sum, that's this right here. That is the general solution of the entire thing. So we have a way of finding the general solution for this big ugly thing. All we have to do is solve the smaller, easier problem of what's the general solution for that. And then the tricky part is what's a particular solution for this whole big thing. So let me give you an example. And it's going to be a little hand wavy at first, but I want you to see how it works. Okay, so we have, for your differential equation pleasure, one big non-homogeneous differential equation. It's got something times y plus something else, right? So there's no doubt about it. This thing is non-homogeneous, but buried within it, we have this little part right there that is totally homogeneous. And it turns out we just solved that. So we know what the general solution is. So off to the side, we know, because we just solved it, that y of t equals some constant times e to the sine t. We know that is the general solution of the associated homogeneous, I'm abbreviating, I hope you don't mind, differential equation. Right? We just found that on the previous page. So part of this big honkin' mess we know how to solve. So what we need now is we need some particular solution for this whole thing. So down off to the side I'm going to say, so imagine, just for right now, that we know y equals t over 5. That is a particular solution. For the entire non-homogeneous differential equation. Imagine that's the case. If that's true, then we have an equation for, oh, I'm going to say not so, I'm going to say then. Then y of t equals, we would take the general solution that we have for the homogeneous part, and then we would add the, let me get the other color here, particular solution that we were just given. This, oh, I don't want to keep writing in green. This is the general solution for the whole thing. And I know you're sitting there thinking, wait a minute. How did you, just wait. Let's verify it before we go too far and make sure that we did it right. So I'm going to borrow another color here. So let's verify. We're going to verify, and I'm going to write it out more plainly here. We're going to verify that y of t equals my original general solution for the homogeneous part, c e to the sine t, plus my particular solution, which was t over 5. So I'm going to verify this is the general solution. And so we'll do that by taking it as the y and plug it in everywhere there's a y in this equation, there and there, we're going to sub it in. So d dt of, and then this stuff right here, and I'll just write it down here, c e to the sine t plus t over 5. Take the derivative of that, that's the right-hand side, or the left-hand side, sorry, and that's got to be equal to cosine of t times, again, the same y, c e to the sine t plus t over 5. plus, and I'm going back up here for the equation, 1/5 times the quantity 1 minus t cosine t. Okay, so this right here appears here and here. That's the y value that I've subbed into my differential equation. So I should be able to continue this process and verify that we get a true statement on both sides. So what's the derivative of each one of these terms? Well, this is an exponential. When I sub this in, I'm going to get the derivative of constant times e to the sine t. Well, that's just going to be a constant times e to the sine t times the derivative of sine t, which is cosine t, plus t over 5. The derivative of t over 5 with respect to t is just 1/5. So that's the left-hand side. The question is that in fact equal to, on this side, when I multiply it through, I'm going to get c times, I'm going to write it like this, and you'll see why in a second, e to the sine t times cosine t plus t over 5 times cosine t plus 1/5 minus t over 5 cosine t. Now it looks like a big honkin' mess over there, but notice a couple of things. On one side of the equation, we have, let me get my red pen here. On one side of the equation, we have an c e to the sine t times cosine t. We have that exact same thing over there. So they would cancel each other out. On one side, we have a positive 1/5. On the other side, they have a positive 1/5. And then these two terms right here, they're actually the same thing. They're just additive inverses of each other. So they kind of cancel each other out. And so what you have is the same thing on the left as you do on the right. So it checks. It checks out. So what we've just done is we've verified that we know that y of t equals c e to the sine t plus t over 5 is the general solution. For the non-homogeneous differential equation. Now you might be sitting there thinking, hey, that's great. That's terrific. All I have to do is solve this part, which I totally can do from section 1.2. That's just separation of variables. And then I just have to come up with a particular solution, something, simple, like t over 5. But of course, if you're also sitting there thinking, how did you know that this was a particular solution for the entire non-homogeneous differential equation? How did you come up with that as a solution? Well, on the next page, I kind of spell it out. It starts off and it says, it's like magic. If we want to solve any non-homogeneous linear differential equation, we got to do 3 things. All we got to do is solve the homogeneous case, which is usually really easy, right? Check. We have to find a particular solution of the non-homogeneous case. Check. And then we add the 2 together. Check. And booyah. It's just like we, cast a spell. We wind up with exactly the right answer. But of course, if you kind of scroll down, how do we do that step 2? How do we do that step 2? Well, it turns out we're going to use one of the most famous and important techniques in all of mathematics. And we'll start that in the next video. We'll keep you on the edge of your seat until then.